Okay, we're back here right away for the second part of dy dx, or derivatives with trig. That's not necessarily the right notation for derivatives, but that's okay. Why? Because we're going to work it out anyways. Okay, so let's look at this first one. As we're doing this, we really want to focus on identifying the form of the problem first. In other words, is it got a quotient rule, a product rule, a chain rule, all of the above, sum and difference. We want to kind of see what we're going to do and then try to fulfill that. So this first one, I notice here that all I really have is a constant times this. So it's going to be that constant multiple rule. So think about dealing with the constant multiple. That means my derivative, f prime of x, would be the proper notation this time. That 3 is just going to tag along. And then we have the derivative of cosine x, which in this case is negative sine of x. Now if I were to simplify that, that negative would pop out front. We'd have negative 3 times sine of x. For this second one here, I notice that I actually have a product rule. I got one function times another function. We'll call these a and b. Remember, you always have a mixture, one original times the derivative of the other. So that would tell us that we'd have a times b prime plus b times a prime. Well, a is sine of x. B prime is going to be the derivative of cosine of x, which in this case would be negative sine of x, plus b times a prime. Well, b is cosine of x, and the derivative of sine of x is also cosine of x. So now simplifying this, I have a negative in the first term, 2 sine of x, so we could call that sine squared x, and just cosine squared x for the second half. So that would be our derivative. F prime of x equals negative sine squared x plus cosine squared x. Easy. Let's look at this next one. Again, product rule. We're doing product rule. We got a product rule going on here because we got two functions. The first one is just t, and the second one is cosine of t. So if we're doing a b prime plus b a prime, let's figure out what that would be. F prime of t equals, well, a is just t. B prime is going to be negative sine of t. And then plus b is cosine of t. And I don't need any more space because what's the derivative of just t to the first power? Oh, it's just 1, so I don't really need to write it. So if I were to simplify this at all, factor out that negative, not factor out, but move that negative a little bit, we'd have negative t sine of t plus cosine of t. Super easy. Okay, this next one, we're adding. Does that really make a difference? No, when you're adding and subtracting, you kind of just treat each term as an individual. You don't got to group them or do any special combination plays with them. They're each their own. So then our derivative of y prime, or dy dx, either way you want to write it, we can do the derivative of each one individually. Derivative of sine x is cosine x. And the derivative of cosine x is negative sine x, so it'll be minus sine of x. Done. Done, dizzle. Move it on. Alright, just for fun, let's call this one dy dx. But before we even jump into that, I do want to notice that here I have a little bit of a chain rule and a constant multiple going on right here. So that 6 is going to tag along, and I have a chain rule where cosine is the first layer and x squared is the second layer. So the 6 is just there, tags along. We're going to take the derivative of cosine, which makes negative sine, leave the inside alone the first time, then multiply by the derivative of that inside layer, which is going to be 2x. The derivative of x squared is 2x. Now if I were to simplify this 6, this negative, and this 2x would all combine to become negative 12x. And then we'd have sine of x squared. Alright, now this one is slightly different. Notice that the squared moved from the x to the cosine, which really means 6 times cosine of x squared. So then y prime, our derivative, that 6 is going to tag along, but now we have slightly different layers. The outside layer is 2, the inside layer is cosine of x. So we're going to drop that 2, change the power to a 1. Cosine of x gets left alone for the first one, but then we multiply by its derivative, which in this case is negative sine of x. So now to combine a few things, we have this 6, 2, and negative again, so it's going to be a negative 12. We have a cosine x and a sine of x. Written in either order, doesn't really matter. And that's our derivative. Super easy. Okay, now we get to some more complex type things. Just for fun, let's change the color up a little bit, just to keep it fresh. So this first one, I want to first translate it. We got that constant here, no big deal. But this cosine squared, that means it's going to be cosine of x squared squared. So then when I take the derivative, dy dx, I'm going to first drop that 2. So we have the 6 is a constant multiple, just tags along. The rest of it's going to be a chain rule. So when we drop the 2, and then this power goes from 2 to 1. We're going to leave cosine of x squared in there the first time. But notice something, I didn't really do this and I should have. 2 is my outer layer, cosine is my middle layer, x squared is my inside layer. So now we got to do the middle layer, which is cosine. The derivative of that is negative sine. We leave the x squared alone the first time. Then we're going to multiply by the derivative of this inside layer, which in this case is 2x. And now we're done because we've done all 3 layers. So let's combine things a little bit here. We got this 2, this 6, this negative, this 2x. Put all those together, we get negative 24x. Then we have cosine x squared, sine of x squared. So cosine of x squared times sine of x squared. There we go. Okay. For this next one, I didn't do it this way in class, but I'm seeing something. I'm seeing, in my head, 1 over cosine of x plus sine of x over cosine of x, which is really secant of x plus tangent of x. That's interesting, because now I've changed it from a quotient rule into a sum or difference rule. And I know the derivatives of secant x and tangent x based on the table I was given earlier. The derivative of secant x is going to become secant x tangent x. And the derivative of tangent x is going to be secant squared x. So when I do this derivative, dy dx, the derivative of secant x is secant x tangent x plus the derivative of the second piece here is just secant squared x. That's really interesting. It kind of simplifies what you were doing without even really thinking about it. So sometimes it's helpful to separate something into 2 individual trig functions. So algebra first might be helpful. Let's look at number 9. We got cosine of x. Not a big deal here, but we do want to make sure that we realize this is cosine of x, all raised to the 1/2 power. That helps me see that when I take the derivative of y prime, this is going to have a 1/2 on the outside drop down. We have a cosine of x left alone the first time to the negative 1/2. So the outside layer done for the derivative. Now I just got to do the inside layer, which in this case is negative sine of x. So if I were to simplify things here to a multiple choice type answer, I could do a dividing bar. I know that I'd have a 2 on the bottom. I'd also have a negative sine of x on top. And on bottom, I'd have this cosine of x within a square root, because it's negative 1/2 power, meaning negative meaning it's in the denominator, or it flips across the dividing bar, it's a reciprocal. And the 1/2 meaning that's a square root. All right, let's keep moving. For this next one, it looks like we have tangent square root of x. In other words, that's tangent of x to the 1/2. So I have the outside layer is tangent, the inside layer is x to the 1/2. So when I do the derivative, dy dx, y prime, any one of the above, the derivative of tangent is secant squared. We're going to leave the x to the 1/2 alone the first time. Then we're going to multiply by its derivative, which in this case is 1/2 x to the negative 1/2. Multiplying or simplifying all those pieces, we're going to have secant squared of the square root of x. And then here we'll have over 2 times square root of x as well. Now it's not likely that they would do this, but know that secant squared is really 1 over cosine squared. So I could see them doing this. Why? Just because they like to make things look different even though they're not. 1 over secant squared, secant squared is 1 over cosine squared. So I'd flip it across and then write cosine squared, square root of x here. So either way it could be written this way or this way. But just kind of note those things as we go, and that's something worth seeing, so that when you do see it on a test or an AP exam or in some type of multiple choice situation, you're not really confused. You're like, oh, I've seen that before. Let's look at this. Number 11. Number 11. First plan. Okay, we got layers. This is really tangent. And then we got 5x to a 1/2 power. Okay, so we got lots of layers going on here. This tangent is one layer. This 1/2 is the middle layer, and the 5x is the final inside layer. So let's deal with them one at a time. dy dx. The outermost layer, the derivative of tangent, is going to become secant squared. We're going to leave everything else alone. So it's going to be 5x to the 1/2 power. 5x quantity to the 1/2 power. Now we're going to multiply by the next layer, which is the derivative of that 1/2 power. So it's going to be 1/2 times 5x to the negative 1/2. Then we multiply by the innermost layer, that third layer there, the 5x. The derivative of 5x is just 5. So if I were to simplify all this, I suppose that we could have 5 times, what else do we have here? That's it for the numerator. Everything else could be in the denominator. You could have secant, or not secant, cosine squared. How am I getting this? Because it's secant squared in the numerator, therefore cosine squared in the denominator of the square root of 5x times, oh well, we got this 2 on the bottom. Let's put that up front. And then we got this 5x to the negative 1/2. So that's the square root of 5x again in the denominator. Okay, last one, and we'll go and pause the video again, move on to part 3 here. So for this one, it says y equals secant cubed. That means secant of 2x plus 1 quantity cubed. So that's what our function really is. So now if we're trying to identify these layers, I see this cubed as the first layer, secant as the second layer, the middle layer, I guess you could say. And 2x plus 1 is that third layer. So let's start out with the outermost layer, y prime equals. That 3 is going to drop out. Then we'll have secant 2x plus 1. This is going to be squared now, because we dropped the 3, so we also subtract 1 from the power. we're going to multiply by the derivative of the next layer, which was secant. Well, this is going to start getting kind of big here. So we're going to have secant, tangent, both having a 2x plus 1. That's too big. Let's make some more space. Y prime equals. So first we have that 3 times secant 2x plus 1 quantity squared. Now we're going to have secant 2x plus 1 times tangent 2x plus 1 times the derivative of the last layer, which is 2. Whew, that's long. Let's simplify. This 2 and this 3 are constants. They can be combined to make a 6. Now I'm going to have secant 2x plus 1 squared. So I still have to have that. Secant quantity 2x plus 1 squared. Or secant squared, I guess. Right. Then we have secant 2x plus 1 times tangent 2x plus 1. But wait a second, I see secant times 2x plus 1 to the second power, and this one's to the first power. I could put those together, and this would become secant cubed 2x plus 1. We got this 6 out front. Times tangent 2x plus 1. This is definitely what it would probably simplify to. Definitely, probably, definitely, maybe. Alright, so I'm going to pause the video there and make a part 3. We're going to keep these ones short so that you can kind of piece it out a little bit.